Hello everyone, welcome back. In this lecture, we will discuss practical issues involved in decision tree learning. We'll first discuss overfitting, which is an important thing to consider in any machine learning model, also in decision trees. Then we'll consider when to stop growing the decision tree. Remember, in the ID3 algorithm, we constructed the tree till we hit a leaf node, but it's often not efficient and contributes to overfitting. So, stopping the tree when appropriate or considering pruning the tree after it has been built can help in reducing overfitting, and we'll look at these two approaches. And then we'll also discuss some practical scenarios where decision trees are used. For example, in data where there are non-Boolean attributes, where there are continuous values, um, how can decision trees be used there effectively, and then handling missing attribute values, which is another practical scenario that could arise, and we have if we have to use decision trees in that, how to go about doing that. All right, so overfitting in decision tree learning. uh, in machine learning, remember that our goal is to maximize the performance on test data. So the training data is used to learn the model, but test data is a scenario, is the application scenario for our model. So we want to maximize the model's performance on test data. So overfitting, when the model is overfit to the training data, it gives you a graph like this, accuracy versus size of the tree. So that if you can see the training data, the accuracy keeps improving, which means that it is overfitting to the training data. And on test data, till some point the accuracy improves, the size of the tree improves the accuracy till 0.75, and then it stays in 0.75 for a while, and then it actually drops and the accuracy becomes lower. So a larger tree does not necessarily mean that it will give a better accuracy on test data. So after a while, it is not beneficial to keep growing the tree. A shorter, more balanced tree could give a better result on test data. So that's why we want to avoid overfitting, always catch instances where we are overfitting, because that is tends to be the primary reason why models don't perform well on test data, even though they perform great on training data. Okay, so overfitting in decision trees could arise from multiple different scenarios. One popular reason why this could occur is when there are noisy training examples. For example, here we have sunny, hot, normal, strong, play tennis equal to no. So this is another training example. If you want to add this to our already existing training set, then if you see here, sunny, outlook is sunny and the humidity is normal, that actually has the decision yes. And now with this new example, outlook being sunny and humidity is being normal, would have a play tennis decision of no. So now we, with this branch, with this path, outlook being sunny, humidity being normal, has been selected as for a decision of yes. But now with the addition of this training example, we have to again split this path and add another node to split on, so we can now decide between these two examples where the same attribute values have the decision of yes and no. So to do that, now the tree will become more complex, more it'll be deeper, and more nodes will be added to just address this example. But this example could be a noisy training example. By noisy, it could be, what I mean is, the play tennis value could have been recorded wrongly in the training example. Then you are building the tree based on the fact that all the training examples are actually correct. But this noisy training example can throw the tree off, and can cause you to split and build deeper trees, longer, deeper trees, and for just fitting the training example. But when it comes to test data, this deeper tree will not really be meaningful because there were noisy training examples. So, formally defining overfitting, if there is an error that you measure on training data for your constructed tree, which is hypothesis H, then you have D, which is the entire distribution of data. So hypothesis H overfits the training data if there is another hypothesis H prime such that the error on H is less than error on H prime in the training set. So in the training set, H performs better than H prime, but in the entire distribution of data, D, H performs worse than H prime. So there is another, so this is similar to what we discussed in overfitting. We had different kinds of models with varying complexity, right? So here again, H and H prime are two trees. Consider there are two trees. And on the training set, one of them performs better, which is H, and H prime performs worse. But H prime actually performs better on the entire distribution of data, or we could also say it performs better on test data. So that just means that H has overfit the training data. That's why it's not able to generalize well to the entire distribution of data or to test data. Okay, so we saw that noise could be a source of overfitting. There could be other reasons to why the decision tree would overfit to your training data. Remember, in the ID3, we are building till we reach a leaf node. What if there are fewer examples associated with a particular leaf node, which also could be a signal that the tree has overfit the training data. For example, I'm going to go back and look at the tree just to give you an example. So let's say, let's consider the leftmost branch in the tree. Outlook is sunny, humidity is high, and the decision is no. So let's say if this branch and this leaf node right there corresponds to only, let's say, 2 or 3 data instances. We had, I think, 14 data instances, but in a real world data set, let's say you have 1,000 data instances, but you have less than 10 in this leaf node, then that would be a low number. That would be a low percentage of the data that this particular branch in the tree classifies. And so you're wasting this entire branch on the tree for very few data instances, and that may not scale when it goes to the test set because you may not have so many instances, because this seems like a minority, right? Seems like these combination of attribute values is not so common in the training data set, and it could be even less common in the test data set, and it could hurt your accuracy. So if there are fewer examples, and it could also be the case that there is only one example associated with a leaf, because remember the decision tree, when we are building it, it will keep building the tree till the leaf becomes pure in the sense that it has only one decision, either no or yes. So it could just happen that there's just one instance that the whole path is corresponding to, and that could just hurt your performance in the test data. Generalization is key. Generalization is the most important thing in machine learning, because you don't want a model which performs great on training but does not perform well on test. Optimizing for test is key, but you don't know test instances until test time. So you cannot look at them in advance. So you are going to only work with training, but if you overfit, then the ability of the model to generalize to test reduces. Okay, so there are two approaches to avoiding overfitting in decision trees. The first one is stop growing the tree when the data split is not statistically significant. So you calculate some kind of significance before you split, before you add an attribute to split on in the tree. And if it turns out that it's not statistically significant, you stop growing the tree. The second approach is grow the tree fully till you reach the leaf node, till every leaf is pure and it's completely all training examples can be exactly classified. Grow the tree fully and then prune the tree. This both these approaches are used. Post pruning is more preferred because not growing the tree or stopping to grow the tree before you grow it fully is a more pessimistic approach, and you don't know how the tree is going to be after you fully grow it. It may as well be that the tree is not deep and not completely imbalanced. It can be that it is not going to do that, but you are pessimistic and you're stopping to grow the tree beforehand. So you have not really explored the space, explored all the attributes that you may want to split on, and constructed the tree fully. So often that does not practically give you better performance. So post pruning is usually preferred from a performance standpoint, but both are used according to the situation. All right, the key issue is what is the correct tree size? The correct tree size is not really clear. It depends so much on the data. It depends on the test data, which you do not know. So there are so many variables that you don't know, so many that you know, but still you may not be able to optimize for 100%. So balanced trees are preferred. Trees that are really long on one side, that have one path that is too deep, but others are shallow. That's an imbalanced tree. Those are generally not preferred. Trees that only grow on one side and the other side they don't grow much, which is again imbalance, but there's a huge imbalance. There's one side which is too deep, and another side is not, is too shallow. Those are generally not preferred. And Too many splits just to reach very few instances, just to capture very few instances. We already saw that that's not really ideal. So these are things to look for, and these are more qualitative than, I mean, they can also be quantified, which we will see in these slides. But when you build a tree, I'm an intuitive person, and I like to see what trees get built and like to understand how they look and how that corresponds to performance. And that's what I'm trying to give you, the intuition of how to select a good tree. And when you see too many splits going in one direction, too many splits being made just to classify very few number of instances, these are ways when you can catch that the tree is going is overfitting and is building in the wrong direction, and maybe you can stop the tree. So, or maybe you can look for those parts when you prune the tree. So this is some intuition that you can use. And right, the first thing that we'll see, first way to avoid overfitting, is the chi-square test. It's a statistical test. It can actually use other statistical significance tests as well to see whether or not expanding a particular node or splitting it, adding another node in this particular path would be helpful and would provide an improvement in your prediction. And you can also add a complexity penalty. So you can penalize trees that are long, that are splitting again and again. So in the process itself, you can actually penalize it, and that could help. And you can also use a validation set. That's another thing that it's a running technique for overfitting. It's not just relevant for decision trees. We're going to introduce that here later in this lecture. Okay, the first technique is chi-square pruning. Chi-square pruning builds the entire tree. You can also use this to stop building the tree, but we'll discuss this scenario where we can build the entire tree and consider the decision and consider the each leaf decision and perform the chi-square test. Okay, how do you perform the chi-square test? So you have let x be an attribute that is in your tree, and x has number of instances entering small s. Number of positive instances entering the decision is p. Number of negative instances entering this decision is n. So that's being fed into x. So x has whatever is entering x is total s and positive p and negative n. And after x splits into its attribute values. So the attribute values of x, let's say, are capital F and capital T. So it's similar to, if let's say x is outlook, then F could be sunny and T could be rainy. So these are attribute values of x. So remember how we split the decision tree, right? So when you introduce an attribute, you split based on the attribute values. So capital F and capital T are the attributes values. And for, let's say, for capital F, where x is equal to capital F, you have S subscript F, SF, or the total number of instances, where capital X is equal to capital F. And PF are the number of positive instances and that are in this branch, NF or number of negative instances in this branch. Similarly, you have for x, capital X is equal to capital T, you have ST, total number of instances, PT, total number of positive instances, and NT, total number of negative instances. Now, so it's a significance test. So you're going to go with a hypothesis. The hypothesis is that x is uncorrelated with the decision. So you're saying that x is not correlated with the decision, it's not contributing to the decision. So which means that your number of positive instances, PF, after the split. So after the split, you get PF here, right? On the left side, on the left branch. So number of positive instances, PF, after the split is close to the scaled version of P. So let's say P is what is entering. So P by S is the ratio of positive instances that are entering X to the total number of instances that are entering X, right? P by S is that fraction. Scale it with the number of instances where X, capital X, is equal to capital F. Then you get, if that is close to PF, then you have not, the split has not really made any difference. Let's say if 10 instances are entering, I'm just going to take some numbers to explain this. 10 instances are entering, and then 5 of them are in capital F, and 5 of them are in capital T. So x equal to F is number of instances where x equal to F is 5. Number of instances where x equal to T is 5. Now, if we see that PF after the split is close to 2, then 5 out of 10 and 2 out of 5 both are sort of same, 0.5-ish. Then that would mean that the attribute X is not really splitting the data and making it purer, where you actually have fewer on one side and more on the other side. Your ratio remains sort of the same. So you calculate the ratios for PF, PT, NF, and NT, and if they are similar to the original ratio that existed before the split, then the split did not really do much, and that split can be disregarded. So that's how you can identify nodes which are not doing great splits, which are not really changing the ratio of the positive instances and negative instances after the split. So that is how you can identify these nodes to remove. Okay, the second and more popular way to do decision tree pruning is using a validation data set. So validation data set is a data set which is used only for tuning and making your model better. So it's sort of similar to a test data set in the sense that you don't train on it, but it's available at training time only for improving the performance of your training data. And then there will be a separate test data set on which you will test your model, and that test data set is completely hidden from you and you don't know how that looks. So when you get training data to train your model, typically what we do is that we split 2/3 of the data and use that for training the model, to learning all the splits and constructing the tree. And 1/3 of the data we keep that aside. And when your model is built and all ready, then you use the trained model on the validation data and then see how it performs. So suppose on training data set you get 0.95 accuracy. On validation data set you get 0.9 accuracy. What does that mean? That means your model has overfit on the training data. So you know that because your accuracy has dropped from 0.95 to 0.9 when you tested it on validation data set. Now what do? You go back, you prune the model, you make the model different. Now again, and use the training data to do that, and then again you run it on the validation data set. And now you get a new number. And keep doing that till your validation performance is better or closer to your training data set. And then you can pass the model as your trained model and then compute the scores on the test data set. And why does this work? This works because when you do this random split, you can see that there is less likelihood of both the training dataset and validation dataset to exhibit random fluctuations. So you are trying to reduce that by splitting it and using one to evaluate the performance of the model and fine-tune it. And a practical limitation here is that it should be large enough to serve as a safety check. If you have very few data instances, and oftentimes this does not work so well because you are now training on even fewer data instances, and that's not really ideal for the model. It's not really learning that much, and then it would hurt performance nevertheless. So you need to have a sizable data set for this to happen. For example, I can give an example from an NLP task. So in NLP tasks, generally annotated data is hard to come by, so you have fewer instances. We have had cases where we trained with 200 data points, 100, 200. That's definitely on the low side. 1,000 people would say it's still low, because in this day and age, you can generally get larger data, and models generally tend to work better on larger data because the models are bigger. There's definitely a huge increase in computational power in the recent years. So bigger models, more computational power, and larger training data sets is what we're going towards. But in some domains, it's hard to get. And then in some domains, that's why training and validation split, doing that would be hard. So again, machine learning is theory and practice. Both of them have to come together. So keep these practical things in mind, because when you go graduate from this class and go and use machine learning in the real world, these practical suggestions and practical utilities definitely help you. Okay, now pruning, approach 1. So after you build the tree, using the validation data set, you can prune the tree in 2 different ways. First off, we'll discuss reduced error pruning. This is simpler and it's easier to understand. It's a greedy pruning approach, and if you have taken an algorithms class, you know what greedy means. Well, split the data into training and validation set. We already learned how to do that. And do keep pruning until further pruning is harmful. So that's as simple as that. It's greedy. So take a node out and see if that improves the performance on the validation set. If it improves, then great. Then you keep taking nodes out till the performance on validation data set begins to drop. If it begins to drop, then it means that it's harmful. So then you put it back and then you say that this is my prune tree. So keep taking nodes out till the performance improves. When the performance drops, then you know that the last prune that you did is harmful. So you put that node back and that is your pruned tree. Effects of reduced error pruning. So this is like a practical graph from one practical application. And here you can see that during pruning, it definitely has a more softer curve. So after on test data than before where it actually drops. So it definitely has a higher curve, and for size versus the accuracy, it improves a little bit. Now, for the next pruning method, rule post pruning. So rule post pruning is a really interesting method, and it's often used and it's very effective, and it also removes the bookkeeping of the tree. So you will see how that's done, and then you will appreciate it. Here again, we are building the decision tree, allowing it to overfit. And then we're converting the decision tree into a set of rules. And then the rules are pruned. And then the rules are sorted using their estimated accuracy. And the rule set is returned as the model. So now we started with a decision tree here. After pruning, we are going to end up with a set of rules. We are not going to go back to the tree from the rules. So this is a one-way street. You start pruning the tree. First, you convert the tree into rules. Then you prune the rules. Then you get a set of pruned rules, and that's your model. Okay, how do we do this? Let's consider the leftmost path in our sample data set that we built. So if outlook is equal to sunny and humidity is equal to high, then play tennis is no. So this is our leftmost path, right? So we've been reading it like this, right? That's how you read it. So these are questions, answers to questions, so on till we reach a decision. So that definitely can follow this rule format. That's what we have here. So the leftmost path has this form of a rule. That's how we sort of are anyway intuitively reading it. But now we are just putting it down in the form of a rule itself. So if outlook is equal to sunny and humidity equal to high, then play tennis is equal to no. Now you prune this rule. You take this rule and you prune it. You can now prune any of these conditions, right? If outlook is equal to sunny, that could be removed, or humidity equal to high, that could be removed as well. So any of these conditions that exist before the then. So if there are a set of conditions, right, and they're and or conjuncted together. So you can select any of these conditions and then you can actually prune it. So for example, here each rule is pruned by removing antecedent or preconditions. So what are the preconditions here in this rule? Outlook equal to sunny is one precondition. Humidity equal to high is another precondition. And you remove one of them and then see if that improves the results. What is the inherent advantage of rule post pruning? So each path is one distinct rule. We already saw that. Pruning decisions regarding attributes can be performed differently for each path. So this is the biggest advantage of rule post pruning. So here we are pruning these paths differently. We are not pruning the tree. So for example, I'm going to go back to the tree to understand this. Where is my tree? Oops. Yes, here it is. So here we have, so far we discussed how we could prune the nodes in the tree. If you are going to keep the tree data structure, you have to prune the nodes. So if, let's say, you're pruning humidity, then the entire humidity node goes away, right? So now you actually pruned two paths in the tree, right? So one path where outlook is sunny, humidity is high, and the decision is no. So that's one path. Another path is outlook is sunny, humidity is normal, and the decision is yes. So these two paths both were pruned when humidity node is removed. But on the other hand, when you prune the path, you only pruned that one path. In the other, let's say you remove humidity equal to high here. But the other path could still have humidity equal to high because the paths are treated separately, because each path is one rule, right? You're only pruning the rules. So the other path could still have humidity. So this gives you a richer and more variation, it gives you more flexibility in the pruning process, right? So because you don't need to prune a node and then worry about all the decisions it's going to affect. So you can prune for each path is one decision, right? So you can prune each path separately and not worry about how that would affect other paths. So that is the greatest advantage of rule post pruning. And it also removes the distinction between attribute tests near the root and those near the leaves. Okay, again, I will have to go back to the tree to explain this. So let's look at these. What attributes are here? Outlook, humidity, and wind. 3 attributes. So now if you remove humidity, right, then all the instances that humidity classifies have to go back to the sunny path. And then you have to assign leaf nodes there if you remove humidity. But, so that's some bookkeeping you have to do. You have these instances have to go back. And then they have to be appropriately assigned to sunny by some probabilistic measure, right? Because if you have, let's say, 3 no's and 6 yeses inside humidity, then when you remove humidity, then with sunny, you are going to say that you're either going to count the majority and assign it there, or you're going to have a probability value. Now, consider removing outlook itself. Now the root is removed. When the root is removed, the whole tree has to be constructed again. Otherwise, it's no longer a tree, right? So now you have to pick a new root node, and then you have to have branches coming out of it to other nodes that are existing in the tree and reorganize the tree. So think of how you would do tree deletion in a normal tree data structure. Forget the decision tree. In any tree data structure, you already know a tree data structure, right? So how would you do a deletion in that? So when you delete nodes, you have to assign the instances to other branches, and then you have to assign the links. All those things you have to do for bookkeeping purposes so that you can still traverse the tree, right? Similar things will hold here when you are pruning the tree. So pruning closer to the leaves is much easier. You know that when in a tree data structure, how would you do deletion? Deletion closer to the leaf is pretty easy. But If you remove the root node or closer to the root, then you have lots of other things. You have to assign the nodes differently. You have to lots of links should be removed and reconstructed now as per the new tree, and that is the same thing that happens in a decision tree. So that is the amount of bookkeeping you do in any other pruning. But in rule post pruning, since you're converting the tree into a set of rules and then only pruning the rules, you are no longer doing any of these bookkeeping. So you don't want the tree anymore. You have already converted that into rules, and you are only going to use the rules going forward. So you actually don't need to do any of these bookkeeping and tree organization, tree deletion, and all that comes with it. So that is another really big advantage with using rule post pruning. Right, so reduces bookkeeping issues regarding reorganizing the tree. Okay. And there are a couple of more things that we said we will cover. How do you handle non-Boolean attributes in the tree? So let's say continuous attributes. Can you split them with a threshold, and how to actually choose that split? What threshold do you use? A simple way to do this is sort the value, the attribute values. So here we are using temperature and we are sorting temperature by its value, 40, 48, 60 in increasing order. And then you see for each of these values what is the corresponding decision. For each of these instances, what is the corresponding decision. Then you will see that the first two are play tennis, decision is no in the training data set. Next three are yes, and again no. So now you clearly can see two splits that you have to do, and you can split them at, let's say, some threshold between 48 and 60, and here we have chosen 54. And another one is between 80 and 90, let's say 85, and split on these multiple intervals. And splitting on these intervals makes you discretize your continuous data space into discretize the continuous data space so that you can actually ask these questions. So remember, decision tree is all about these questions. So how would you make it work for you? So if you have a continuous value data, you cannot ask, is the value 40? So that is really not a good question, right? Because it only captures very few number of instances. It's not a generic enough questions that captures lots of instances. For example, if you have, is the threshold less than 54? Then you can hope that there are multiple instances that are in that bracket that will actually come there. So you can discretize continuous valued attributes into these discrete so that you can build a tree efficiently for this. Handling missing values. So attribute values are missing. This is something that happens all the time. Recording errors could happen. Some values may not be available at the time, so they are missing, but you still have to use that attribute to predict. So patient data is one real classic example. You don't expect blood test results for everyone. You don't have all results for everybody at any time point. It's just not possible. So you have to make do with some missing values here and there. So treat the missing values another value. So just say that all missing values are one attribute. So let's say if high normal is your wind condition, and you don't, sorry, high normal was humidity, right? Humidity. Then you say there is another humidity value that is missing. So you just make it another value, missing. And then treat it like that. So you know that the value is missing is just another value in itself, and then you'll see how the tree classifies it. Another idea would be to ignore the instances having the missing values. Let's say you have some records, some data instances where the values are missing, you ignore them. But this is definitely wasteful because oftentimes you don't have so much data to work with and you cannot really throw away data. Assign the most common value. So this is what usually people do when, let's say you have, again, humidity is high or normal, and let's say you have 10 highs versus 1 normal. So high is definitely the more common value, and then there are 3 4 missing values, then you just assign high to it. Assign the most common value based on the class that the example belongs to. So again, here you look at high and normal number of values, but you look at that with respect to the class. Let's say in the class play tennis equal to no, you have 9 highs and 1 normal. In the class play tennis equal to yes, then you have 3 highs and 7 normal. So you have different numbers for both these class, and then you can see that in one class play tennis is no, high dominates, and in another class play tennis is yes, normal dominates. So based on which class the data instance with the missing value is in, you can assign it the most common value based on that class. Okay, so there's also another approach where you can handle missing values using probability. Then here you assign a probability to each possible attribute of A. So similar to the examples before, you can instead of so let's say we already had this example, right, where 9 highs and 1 normal in play tennis equal to no. Now you just say the new value, the missing value in that set to be 9 out of 10 high and 1 out of 10.1 probability it is normal. So you just retain the, instead of assigning the most common value, you just retain that probability that you get. And then you keep that probability when you assign it to the splits. So for example, 9, so then you will have like 9 plus 9 by 10 high and 9 plus 1 by 10 normal. So sorry, 1 plus 1 by 10 normal. So that you keep that probability. All right, so summarizing decision trees, we learned about the representation, how they are built, what the decision tree, how from a table, how to go to the decision tree, what the attributes mean, what the nodes mean. The nodes mean attributes, and the branches are the attribute values, and the leaf nodes are the decisions. How to grow the tree, how to the algorithm, the recursive nature of the algorithm, how the subsets are parsed, and we did some examples. How to choose the best attribute. Information gain, we discussed the most commonly used measure and how to calculate it, to pick the nodes at each point. We discussed then overfitting, which is not just relevant for decision trees, for any machine learning model, and we discussed how to prune the tree. And then we discussed special cases, missing attributes, continuous attributes, how to handle them in decision tree. In practice, there are many forms. We discussed ID3, that's the most common form. C4.5 is another variant that is also used, and but our discussion was focused on ID3. So if you're looking at the book, please read ID3. Thank you.